Hi, speaking is Chakasolo, and my student number is 19777-175. So, according to this, this is my the overview of my structure. So, each 22 kV bus is supplied equally from Matla as well as the Kriel power station, and then this is achieved by connecting buses radially to a common 22 kV bus, which is this one, that matches feeds from both the mentioned above power stations via this tiebreaker CB13, ensuring a 50-50 split power delivery. Substation 1, 2, 3 up until substation 8 22 kV, and also connected via this two 20 kV buses, um, and circuit breakers are used on all interconnecting feeders, enabling safe operations and ability to perform N-1 contingency switching, whereby at least when we lose one feeder or transformer, it doesn't affect the entire system. Each 11 kV substation is also supplied from upstream, which is already being supplied in the balanced redundant way, as already mentioned above. So this is my 11 kV substation, which is connected via this 22 to 11 kV transformers. So this will be substation A, B, C up until substation F, and then substation H and G are fed from the radially connected 22 to 11 kV transformers, which is this one as well as this one, and then substation H and G are also fed via the ring network, as shown here. It's fed from here, and then it's also fed via there, and the circuit breakers are installed on AV feeder, but 22 kV. Yeah, so circuit breakers are installed on AV feeder for both 22 kV and 11 kV substation to isolate faults and perform safe switching during maybe routine operations or during contingency operations, whereby sometimes when we lose one transformer feeder, we can still supply via the tie breaker scenarios. So now in this section I provide a detailed analysis of the short circuit fault level, results for the interconnected distribution network as model for the Matla and Kriel power station using ETAPs. The review covers all primary and secondary bus bars across 22 kVA, kV and 11 kV substation in both normal and N-1 scenarios. Since the 11 kV substation is fed via 22 kV transformer from the upstream substation, in this case this is the 11 kV substation fed from the upstream 22 kV common bus which is now stepped down by this 22 to 11 kV transformer. So for the generated transformers, the primary side fault level equal or are exceeding the 22 kV feeder buses due to the proximity to the Kriel and Matla power station. So I am gonna run that. Yes, so according to this, you can see that the fault level closest to the source is the highest at 24, and the secondary low voltage side value align with main bus bar circuit, confirming transformer sizing and protection is adequate. And then so this, and then also this is for n-1. When I run the short circuit, you'll see the results. So now for n-1, in the n-1 condition, the fault current at 22 kV buses, which is also this one, dropped to around 15 or 16 kA, and then the corresponding 11 kV substation now see fault level approximately 11.65 kA, slightly increased compared to normal due to the distribution of the short circuit contribution paths, which is 11.65. It's actually 16.64. And then according to this, you can see that the fault level is highest near the generating, and the highest fault at the bus bar closest to the power station is the highest. And then fault on downstream 11 kV, the fault are lower, which is appropriate for the secondary protection equipment and transformer sizing. Under the n-1, the contingency fault level of the main 22 kV reduced because of sources is out, because one source is out of service, but the network remains with the same operating parameters. The increase at the 11 substation is due to the effective sharing and redundancy. And also take note that the breaker selection, all the breakers at 22 must be rated above 25 kA, which is the highest fault level, and 17 kA for the n-1, since at n-1 the highest fault it's around 11.65, then 16 here. So that's why the selection of breakers should be 17 kA for n-1. So in totally the 22 kV bus bar, the for under normal operation, the highest fault that can occur is at 24.57 kA, and then the highest that can occur at on n-1, it's this one is 16.16 kA. and that's on the 22 kV bus. And then on the 11 kV bus, the highest under normal operation is 7.13 kA, and then under n-1, the highest fault that can ever occur is at 11.65. And then after this, I'm now gonna show you the so this is on the 22 kV bus on Innova operation, and then for 11 kV the highest fault is at 7.712. Now going to the load flow analysis. So for that, I must come here and then run it. So now for load flow analysis under normal operations, all the main 22 kV buses hold bus voltage of around 94.87 of nominal voltage, which is around 20.87 kV of 22 kV. And then on the 11 kV buses, which is here and then all over, the bus voltage is around 93.0 of nominal voltage of 11 kV, of which is 10.23 kilovolts. And then all substation and feeders remain under planned voltage and load limits. And then it can be observed that there are no significant voltage drops and overloaded equipment. As you can see, the system efficiency balances the power supplied between the generators and the distribution loads. Now going to n-1. So now under n-1, when we simulate, we can see that on the 22 kV bus, the voltage drops to 87.69 of nominal 22 kV, of which is 19.29 kilovolts out of 22 kV, and that's on the 22 kV substation, 87.69, and then voltage drops to 85.74 on the 11 kV substation or 11 kV buses, of which 85.74 of 11 kV is around 9.43 kilovolts. So the takeaways points in this case is that the loss of a major feeder or transformer cause moderate but acceptable voltage decrease, and all substation remain supplied and voltage stays about the standard emergency or design minimums, which is typically 85% of the distribution network. The supply demonstrates solid n-1 security. The network withstands outages of a single feeder or transformer without widespread supply loss, and without widespread supply loss. And yeah, that will be all. Thank you.